We can't shake hands, but
Why not?
Only because I'm
He has a
just
cold.
getting over a cold and I don't want to spread it any. Huh? Well, I don't want to add to your bacteria.
he also has Ebola.
He's going to introduce you.
Yes, sorry.
Okay. If I can get your attention, it is a real pleasure for me personally to host today's speaker. He was my thesis advisor, so we go back quite a ways. But I think the best way to introduce Martin is to just share with you a recollection I had when I first entered college 44 years ago. I was 17 years old. I arrived at the Cornell campus, very confident, very brash, and it was a very turbulent time in 1970. The campus had been rocked with riots, and I, of course, was a participant in the usual stereotypes. I believed that everybody walking around in torn jeans and a shirt with a fist stenciled on the back of it were people who thought outside the box. And everybody else who walked around in pressed shirts were people who were just inexorably stuck in the past. More than maybe even the physics that I learned in my time at Cornell was the education I got about people. And that is these colleagues to whom I ascribed such great creative genius turned out to be not so much. But more importantly, the people who I had assumed were too stuck in the past and very conventional in their thinking turned out to be among the most creative people I have ever encountered, and Martin was one of the foremost among them. Martin was born in 1931 in a very turbulent time in Prague, Czechoslovakia, and because of the onset of the war, the lead up to the war, Martin's family had to emigrate to Istanbul, Turkey, where he lived until 1946, after which he emigrated to the U.S., attended the Bronx High School of Science, and then on to Oberlin for a BA, University of Michigan for a master's, and then MIT for a PhD work. Martin then became, in 1962, a professor at Cornell, where he remained until 1987, after which time he took a position as the director of the Smithsonian Air and Space Museum, a position he held through 1995. Martin is one of the great pioneers in infrared astronomy. He is among a half dozen people who gave birth to the field. Martin pioneered the fields of rocket infrared astronomy and airborne astronomy. And then later in his career, he was a mission scientist on the ESA-NASA Infrared Space Observatory, which performed in the 1990s, and then the ESA-NASA Herschel mission, which just ended a couple of years ago, another big infrared mission. Martin, among the awards Martin has received are Humboldt Foundation Senior U.S. Scientist Award. He's an external member of the Max Planck Society, recipient of the Catherine Wolfe Bruce Medal of the Astronomical Society of the Pacific, and Martin has had the honor of even having a minor planet named after him. I don't know the story behind that. You'll have to ask him. He's the author of over 400 journal and magazine articles, as well as numerous book reviews. He has been the author of 10 books, 4 editions of this well-worn book in my collection. It made it very easy for me to study for my qualifying exam. I figured I only had to know this one book, and I'd be okay. I'm here, so I guess whether I was propelled here or just squeaked through is something Martin maybe can answer better than I. The other books which have received quite a bit of publicity is Cosmic Discovery. Those of you who were at the theory lunch today heard Avi make reference to that book. On a totally different topic, a book about his tenure at the Air and Space Museum entitled Exhibit Denied, Lobbying the History of the Enola Gay. And most recently, In Search of the True Universe, which for those who've received this current edition of Physics Today, you'll see a very nice review, very positive review of the book. So let me just conclude by mentioning not only has Martin mastered the science and the media, but adding to the media credentials, he has been heavily involved in the making of 3 IMAX movies, Blue Planet, Destiny in Space, and Cosmic Voyage, the last of which was nominated for an Oscar. So if that doesn't whet your appetite for the fact that he's somewhat unconventional in his path through astronomy, I'm sure his talk will. Right.
Thank you, Gary. That's very nice. Someone forgot to show me how to turn this on, I think.
It's just a switch.
It's on.
Oh, it's on. Oh, okay. So you can hear me? Oh, okay. That's even better. Okay, well, at some level it's surprising that we seem to know so much about the universe and so little about ourselves. What we learn about the cosmos is based on telescopes, instrumentation, and data processing systems that we calibrate, test under a wide range of operating conditions, and continually monitor to ensure that the data obtained are reliable and fully understood. The process we understand least and calibrate most poorly is how we, the astrophysical community, determine the way the cosmos functions. We are convinced that in our everyday work, we faithfully review the true nature of the universe. But the history of our field shows that time and again we abruptly change course with consequences that reverberate throughout astronomy. These instabilities can have long-lasting consequences in our field because its various phenomena occur on such vastly differing scales as, for example, comets and supermassive black holes. The many different disciplines studying these varied phenomena are parts of a larger network. The effective symbiosis is required to advance our understanding of the field. Can we find ways to manage this unstable system so it best serves our purposes? Astrophysics cannot reject every instability, otherwise we'd never accept any advances. But many instabilities are based on error, and we should seek to control these as well as possible. Is it possible to exert informed control when needed, or would such efforts discourage new insight and debates? We should at least recognize that stabilizing measures do exist in other walks of life to see whether adopting them might advance our understanding of the cosmos. I'm not aware of our community ever having studied these possibilities in depth, but we'll try to show the forms they may take. Nations currently spend billions of dollars a year on astronomy, even as many people go hungry. Astronomers thus share a responsibility to spend funds allotted to us wisely. I'll first give a few historical examples of instability, each distinct from the others, to show how they assert themselves. First, an example that played out many years ago, mainly in Pasadena, California. In 1917, when Einstein created his general relativity and cosmology, he, like everyone else, imagined the universe static and immutable. Today, we'd say its Hubble constant was 0. In 1929, Edwin Hubble estimated the redshift of galaxies to be 530 kilometers per second megaparsec, though he didn't think this implied actual expansion. By 1952, Walter Baade revised this down to 250 in these same units. An earlier mix-up of two types of Cepheids had misjudged galaxy distances. 4 years later, Milton Humason, Nicholas Mayall, and Alan Sandage lowered this to 180, partly by correcting a previous misidentification of ionized nebulae as hot stars. And in 1958, an even more thorough analysis by Sandage led him to revise this value down to h equals 75. with an uncertainty of a factor of 2. He later dropped this to h equals 50, but today's best estimates cluster around 70 kilometers per second megaparsec, suggesting an age of the universe of order 14 billion years. Now, when parameters such as the Hubble constant change, repercussions cascade through all of astrophysics and its individual disciplines. If one proceeds counterclockwise from the top in this figure, taken at face value, the difference between 530 and 70 kilometers per second megaparsec increases the age of the universe here by a factor of 1 over h, more than a factor of 7. The cosmic number density of galaxies decreases by a factor proportional to h cubed, about 430. It's around here. The mass density of galactic matter in the universe drops in proportion to h squared, roughly a factor of 57. A drop of 57 in the baryonic density drastically alters calculations on the primordially produced ratio of helium to hydrogen. The relative abundances of these two elements observed in stars today then affects not only our estimate of the additional helium produced through hydrogen burning in stars down here, but also the expected ages of stars. These ages and helium contents in turn determine the history of cosmic heavy element production on here, as judged, for example, by the relative abundances of the elements in solar system meteorites up here, which also constitutes much of the evidence we have for the abundances of elements deep in interior of giant planets. Note here the domino effect of cascading information or misinformation. These different subdisciplines of astronomy arrayed around the circle need to harmonize their findings to produce a coherent overarching worldview. The system should accept new findings if they're properly vetted, but reject them if they may be erroneous. We then need to ask how risky it might be for a discipline, say one dealing with planetary interiors, to become unstable by adopting a Hubble constant or some equivalent parameter that may subsequently be found to have been faulty. Are there better ways to do this than we currently employ? The answer, I believe, is yes. Risk assessments of the kind have been made by the ecologist Robert May, who investigated a variety of systems. A diagram of the type he and a co-worker produced may be helpful. In this figure, we see the impact of adoption by the planetary interiors discipline of a particular fraction f, shown as a coordinate horizontally, of cosmological data widely available. Theta, which is shown on the vertical axis, is a measure of the error in these data. In the absence of any countervailing influences, the loss to the discipline will be the product f theta. But this loss may be reduced or diluted if the Hubble constant is constrained in just a fraction of the data, n times smaller than f. This is the fraction 1 over n, fraction of f theta constituting the Hubble constant. And if the discipline has some kind of defense mechanism able to discern and compensate for all but a fraction delta, which are defined right here, of the error of the total loss to the discipline, which then becomes delta f theta n divided by n down here. This figure is based on the actual ecological system May investigated, the network of investment banks that led to the failure in 2008 of Lehman Brothers, followed by the collapse of other major banks. You can see the parallels. If a bank acquires a fraction f of the stock in some venture X, shown along the horizontal scale at the top, and if the risk theta is unit to the bank is certain to lose all of its investments f. lowering the level of risk as well as the size of the investment can protect the bank's holdings. Although I've only shown the risk the adoption of tainted data entail, later in the talk I'll propose means by which astronomical disciplines can attempt to protect themselves against adoption of bad or misleading data. A second example of instability shows how and why the introduction of new theoretical approaches can be just as destabilizing as novel observations, for good or for ill. This is particularly well documented for the inflationary theory of cosmology. Proposed by Alan Guth in January of 1981 and soon modified by Andrei Linde, inflationary theory gained almost instantaneous acceptance. By the end of 1981, 15 refereed journal articles had cited Guth's January paper that year. Another 75 referred to it in 1982, rapidly rising to 150, published in 1985. In a matter of 4 years, inflation had displaced a theory in which the Friedman-Robertson-Walker cosmos had been viewed as expanding adiabatically almost since the cosmic creation. Inflation accounted for the homogeneity and isotropy of the universe, explained why space is flat rather than curved, and why the cosmos today is devoid of magnetic monopoles. Homogeneity, isotropy, and flatness had seldom been viewed as serious problems, although Princeton's Robert Dicke had listed all three as favoring an eternally oscillating universe. But inflation's claim of accounting for the absence of magnetic monopoles seems puzzling. Never observed in nature, magnetic monopoles were mainly particles proposed by grand unified theories favored by high-energy physicists. Surprisingly also, inflation violated conservation of energy in precisely the same way as Fred Hoyle's formulation 3 decades earlier of steady-state cosmology, a theory these same physicists had mercilessly derided at the time for not conserving energy. So why was inflation accepted so readily in the early 1980s? An explanation emerges from 400 pages of interviews that Alan Lighton down at MIT conducted individually with 25 leading astrophysicists later that same decade, the 1980s, over a period of about 2 years. A quarter century later, these interviews still offer informative insight. This is the book of interviews. In the interview with Lightman, Sander Faber of UC Santa Cruz, Margaret Geller here at Harvard, and Jerry Ostreicher consistently pointed out that the universe appeared not to be as flat as inflation demanded. The cosmic mass energy density seemed at the time to be an order of magnitude too low. But this didn't seem to worry the inflation's proponents. Dennis Sharma from Trieste was troubled by inflation, half a dozen different variations, and the lack of a reasonably grand unified theory of cosmology formalism. He added, quote, "I'm not saying therefore the idea is wrong, but it's a mess at the moment." Roger Penrose of Oxford, these are all in the interviews that you'd find here, okay? Roger Penrose of Oxford worried that the particle physicists were not sufficiently concerned about the problem of quantizing general relativity. Don Page in Alberta and Robert Wagner at Stanford had similar concerns. Cambridge University's Martin Rees, however, noted that inflation could have started sufficiently late so that quantum gravity need not have been a problem. He recalled that Alexei Starobinsky in the Soviet Union in 1979, a year earlier than Guth, had suggested a quantum transition between an early de Sitter and a later Friedman universe, similar to that of Guth. Joe Silk of the University of California at Berkeley pointed out that inflation still had trouble getting the right amplitude of the microwave background fluctuations. Princeton's Edwin Turner commented that inflation was, quote, "a model that allows one to do lots of cute calculations. It's a theorist's gymnasium, so to speak, where one can go, and there are lots of nice problems to be worked out. Naturally, people do. There's nothing wrong with that, but I think it gives the impression that the theory is likely to be right, or that the field is more important than maybe it is. Jim Peebles, also at Princeton, noted that in the absence of any other idea, a good idea will capture the field. It doesn't mean the idea is right. We should be careful. Reasonable chance we've been led down the wrong path. Certain has happened before. If most of the leading astrophysicists were so lukewarm about inflation, who among those interviewed actually supported the theory? David Schramm of the University of Chicago probably was the most enthusiastic advocate. By 1980, he had already written a series of influential cosmological papers emphasizing particle physics. He recalled, quote, "When I heard about Allen's inflation idea, suddenly everything fit together. Right away I was enthusiastic about it." But aside from Schramm and Stephen Hawking, who also had been active in developing aspects relevant to inflation, most of the senior astrophysicists and cosmologists interviewed appeared to be watching from the fringes. So why was the inflationary model so rapidly accepted and alternative models sidelined? I believe the acceptance came about because high-energy particle theorists saw Guth's work supporting their then-current theories. In 1977, Sidney Coleman here at Harvard had postulated that the vacuum could exist in two different states. A false vacuum at a high energy could jump into the lower true vacuum state with the release of enormous amounts of energy. Cosmologically, he argued, this could have cataclysmic consequences. 3 years earlier, in 1974, two of Coleman's colleagues, also here at Harvard, Howard Georgi and Sheldon Glashow, had proposed a grand unified theory which would combine the strong electromagnetic and weak nuclear forces into a single force at extremely high temperatures that could have existed nowhere except in a fantastically hot primordial universe. By 1979, however, the Georgi-Glashow theory had suffered a crippling setback. It had become clear that it would flood the early universe with massive magnetic monopoles that would persist forever in a Friedman universe merely expanding adiabatically. Yet no monopoles had ever been found. Guth's inflation rescued the high-energy community from having to abandon its favored theories. Inflation expanded space so enormously that most, if not all, of the primordial magnetic monopoles would long since have been expelled beyond our cosmic event horizon. Moreover, the high temperatures prevailing in Guth's early universe promised the physicists a cosmic laboratory for studying physics at energies far higher than terrestrial accelerators could conceivably ever produce. Inflation thus was a cosmology invented by high-energy physicists, theorists, publishing in journals devoted to high-energy physics. Astrophysicists accepted inflation more or less passively. They rather hoped the physicists might bring with them tools to study the origins of the universe and perhaps even explain why the cosmos consists of matter to the exclusion of antimatter. Within a few years, inflation had become astrophysical lore. The cascade of modifications the theory imposed on almost every astronomical disciplines, dark matter studied, galaxy cluster formation, the structure of galaxies, star formation scenarios, continues to reverberate throughout astronomy. The results of the most recent WMAP and Planck missions attempt to provide a measure of assurance that everything we know fits together rather well in such a concordance model. I show in this figure here results published just this past year, about a year ago, by the WMAP group. And you may note that the small potential errors implied by the similarity of the numbers in the last two columns. on the right here. In this table, ignore the fact that neither column takes into account how little we currently understand the nature of dark matter and dark energy. With our current lack of insight on these terms, on these forms of matter and energy, we may still need to brace ourselves for severe shocks ahead. So far, it may have seemed that major turns in direction pursued in astrophysics, even if due to occasional errors or impetuosity, were at least determined by the field's own members or sometimes by helpful physicists. But even this is hardly true, as I will now talk about. As a community, we carry in our heads a landscape, a communal view of the universe. This astrophysicist landscape mirrors the interactions of stars with their surroundings, the interplay of galaxies within their clusters, and our heritage from an earlier phase in the evolution of the universe in which some of the lighter chemical elements common today were first forged at temperatures of billions of degrees Kelvin. The everyday task of the astrophysicist is to gather additional information and make the new pieces of observational and theoretical evidence fit neatly into this landscape. Each newly gathered piece of evidence clamors for a place but often will not fit. To accommodate it, other pieces have to be moved around, and so the landscape continues and continually changes. Although we often think it is, this landscape is not totally isolated. Evolution in apparently unrelated activities normally does not intrude. They're fairly isolated. But when those activities grow beyond a critical point, they may abruptly force their way into the astrophysicist's landscape, drastically affecting its structure and subsequent evolution. Between 1963 and 1970, the United States launched a powerful gamma-ray sensing Vela nuclear test detection satellite systems designed to detect illicit Soviet nuclear bomb tests in outer space. This soon detected bursts of gamma rays sporadically arriving from unpredictable directions far out in the cosmos. They weren't bursts from nuclear bombs, but what they were, the astrophysical community would not determine for another 2 decades. In this Cold War era, other discoveries in newly accessible wavelength ranges pioneered by the military time after time similarly reconfigured the landscape. Each major discovery came as a surprise because the landscape previously assembled had meticulously attempted to exhibit coherence, leaving little room for unexpected external influences. I think I've lost, oh no. Yet there was nothing haphazard about all this. As World War II was ending, President Franklin Delano Roosevelt had encouraged the planning of a post-war program of scientific research. This task had been proposed by Vannevar Bush, a former dean of engineering at MIT and by then head of the Carnegie Institution of Washington, who had been recruited to head the wartime Office of Science Research and Development. During the war, his office had overseen the construction of the first atomic bombs, the development of radar, as well as the production of DDT and the medical miracle penicillin, which drastically reduced military death rates in World War II. The document Science, the Endless Frontier that Bush now commissioned was crafted by some of America's finest scientific, engineering, and legal minds. Taking its cue from the successful pattern of research that had benefited the U.S. in time of war, the document recommended a peacetime effort on a similar system of coordinated scientific research on problems of national interest. This benefited astronomy throughout the subsequent Cold War years. The armed forces were willing to provide research astronomers some of the most powerful radio, infrared, X-ray, and gamma-ray sensors developed for military surveillance. With these entirely new branches, of astronomy sprang up across the electromagnetic energy range. Even today, they produce discoveries at a breathtaking pace. But novel technologies are not the sole external influences that shape the astrophysical landscape. Mathematical models of the underlying cosmic topology, geometry, and the ability to compute complex interactions or analyze vast accumulations of data also lead to new worldviews. Physics, chemistry, mineralogy, biology, as well as financial crashes, natural disasters, national policy directives, or wars all predictably alter the course of science as well. Certainly governmental decrees and support, often based on a nation's current economy or military priorities, can command new directions of research. Control of the purse channels scientific projects. Investigations that look promising are dropped for lack of funding. New projects are started because they can be financed. Astronomers then have little choice but to adjust to remain productive. A seldom discussed question raised by all these external influences is the extent to which our understanding of the universe may be shaped by these intrusions, and in particular by the tools that we've inherited. Most astronomers argue that these tools do not influence how our community now portrays the origin, structure, and evolution of the universe. Yet asked what we do, we tell you we are radio, infrared, X-ray, or gamma-ray astronomers, thus betraying the military origin of the tools that we employ in our everyday work. How can we trust what we learn about the universe when it so crucially depends on the tools we were offered by military or industry flush with money? Does a cosmology and understanding of the universe exist that does not depend on how scientists are funded, have access to tools, and develop a theoretical framework that encapsulates their findings? It's hardly conceivable that our understanding of the universe is not driven by the tools we employ. We know this because we were there once before. In the years leading up to World War II, astronomy was driven by just one set of tools, those of optical astronomy. Popular books written before 1939 and the outbreak of World War II depicted the universe in majestic terms. Occasionally a nova or an overpoweringly larger supernova explosion punctuated the proceedings in a display of random, distant fireworks. But the overall impression was one of infinite serenity. Since some of these books were written by leading astronomers and astrophysicists like Sir James Jeans, we may surmise that they largely reflected the views of professional astronomers. These pre-war conceptions of the universe dramatically differ from the views we hold today. Yet what we understand now comes from piecing together the observational results delivered by just some other set of new tools, perhaps not quite as limiting, but nearly so. To be sure, we know much more now than just before the onset of World War II, but except for the gravitational influences they exert, we remain ignorant of dark matter and dark energy, contributing 96% of the cosmic mass energy density. How much would our insights on the universe differ today if military research or industrial efforts of the post-war era had focused on exploring these two forms of energy rather than electromagnetic radiation, and had handed down to us astronomers the tools developed for those specific searches? It's difficult to believe that our views on dark matter and dark energy and on the universe would then be anything like those we take for granted today. Having shown these three examples of how destabilizing intrusions assert themselves in astrophysics, let me now turn to ways in which these instabilities may be at least partially managed. All three examples I gave had broad consequences for the coupled network of astronomical disciplines cross-linking cosmology to the study of galaxies, stars, and planets. Some level of control over this network is therefore desirable. Network control has recently been analyzed by Jean-Jacques Slotine, a researcher in robotics, nonlinear control and learning systems down at MIT, working together with Northeastern University's pioneer in network theory, Albert Laszlo Barabashi, and his colleague at Northeastern Yul Yu. To assert full control over a network, all of its links must be directed. Here is a directed network. In this particular image, all the links have arrows pointing in just one direction, giving it the name directed network. Two head arrows, as shown in this plot, must be avoided if full control is to be achieved, but a circuitous route back to individual nodes, as in the sequence going here from E to C to D and back to E in this network, that is permitted. You can still get full control with that. In a controllable network, no node can have more than one superior or one inferior node. If this happens, additional switches are needed to control the network. Here, node B has two superior nodes, F and E, and node E has two inferior nodes, B and C. Additional switches shown here by crosses are then required for full control. Such stringent requirements certainly are violated in virtually all of our community's interaction with funding agencies, which are replete with two-dimensional arrows, as shown in this governmental network affecting NASA decisions. So it's worth having some sort of systematic plan to see our most desirable projects brought to fruition. Shown here is the structure of the network the U.S. community faced in seeking to establish the system of the four great observatories, the Compton Gamma Ray Observatory, Hubble, Chandra, and Spitzer, which have served our community so well. It took 3 years for an advisory committee established by Charlie Pellerin, head of NASA's Astrophysics Division, in 1985, to convince the agents in each of these boxes, shown here, to reach agreement so that all the arrows finally pointed in favorable directions. And the go-ahead was given first to what became Chandra and later Spitzer. Compton and Hubble had been previously approved by Congress, but the government had been reluctant to approve the last two of the four observatories before even the first of them had been launched. Not unreasonable, perhaps. Any number of people here at CFA were involved. George Field, who had headed the Decadal Review of 1980, Erwin Shapiro, because CFA would be so heavily involved. I think no one spent more time walking the halls of Congress than Harvey Tannenbaum to make sure that what's called AXAF at the time, now called Chandra, would be approved in time. Eventually, Bill Graham, the president's science advisor, in the box on the upper right, became an enthusiastic supporter, and gradually all the boxes in the chart gave approval. So that was good. A comparable organizational chart shows how difficult it is even for a given single U.S. astronomers observing program to be approved, however. You start at one end over in the lower left, and you hope to end down here in the middle at the bottom. Okay? Hope your proposal passes all the hurdles to reach its intended destination. Notice how closely this organizational chart resembles the layout of a pinball machine. With insights on how the system works, it may be possible to effect a favorable rather than an arbitrary outcome. Now let me turn to a network structure that does permit predictable results to an extent possible, and either fortuitously or through experience or unusually perceptive foresight has adopted the traits that Liu, Slotine, and Barabashi subsequently recommended just 3 years ago. To explain how this works, I need to take a slight detour. It concerns the repair of a spacecraft that has suddenly stopped working somewhere far away, out in space. Although most scientists are unaware of it, complex space missions tend to fail in major or minor ways every week, if not every day. The myriad interactions of the many thousands of discrete parts required to keep the mission operational are so complicated that the bizarre failure modes cannot be fully anticipated. So a pattern of experts needs to be on call at all times to quickly invent a temporary fix and then restore the system to full health. All this to repair spacecraft 1 million miles from Earth. The top priority is a correct diagnosis. Let me still wait with this figure. Top priority is a correct diagnosis. You might not guess this, but vocabulary is the crucial commodity. Assembling the right experts, therefore, requires exceptional care. Each space mission creates its own language. In the mid-1990s, the European Space Agency launched the Infrared Space Observatory, ISO, a nearly billion euro mission. By launch, a list of roughly 1,500 acronyms constituted its dedicated language. Although each expert must be deeply familiar with the whole realm of functions, he or she must also be able to fully comprehend at least 2 other panel members communicating through these acronyms, each an expert on some other spacecraft function. Each panelist thus has to have 2 incoming and 2 outgoing links. Let me explain in a deliberately stylized way why this is needed to reach results. Let's say the spacecraft went dead 3 hours ago. The panels sit around a table. Expert A at the top begins by asking whether the failure just discovered could be due to a particular circumstance. Expert E, on the lower left, understands the message from A and thinks that expert D might have an answer. To transmit A's question to D, who would not understand the question directly, E transmits the message through I to D. The conversation always progresses from a panelist to the nearest colleague, able to rephrase it for the next recipient to also comprehend. The messages follow directed arrows, just as Lewis, Lotin, and Barabashi demanded. Expert D now answers A and does so through K to F and on to A. Within a maximum of 5 or 6 steps, all members of the panel can receive any message or its response, and to also receive 2 versions by separate paths, shown here in blue and red, to confirm that the 2 messages agree. If they differ, further clarification can be requested until full agreement is reached. This may appear to be an unnecessarily unwieldy stylization of how an actual, rather more messy panel discussion proceeds, but too much is at stake in repairing a billion-dollar mission. It has to be done right. Each expert has to be confident he or she has given a correct diagnosis. A similar round table of experts, each mastering only one other language, say the language of the expert seated to his or her left, requires, as shown in this diagram, 12 steps for a message to reach every panelist, adding potential errors in transmission and providing no cross-checks. A far riskier procedure. This is why each panelist needs to be conversant with at least 2 other areas of expertise. Now, how does this experience apply to astrophysics? A similar round table of disciplinary experts in which each participant is conversant with 2 other disciplines can help us understand how each of these disciplines is affected by a new discovery, some of whose initial findings may be erroneous and need to be weeded out by multidisciplinary panels to detect discrepancies or contradictions with existing knowledge. and reach a resolution. In practice, this is seldom pursued, but should be. To deal with the earlier discussed changes in the Hubble constant, an assembled panel looking something like the one shown here could have been helpful for sorting out the myriad implied consequences of the changing Hubble constant. Such a panel might have reduced the impact of errors by a factor delta, which I defined up here, fraction of error unrecognized and uncompensated, by which, as I suggested earlier, losses due to suspicious-looking data can potentially be reduced. In 1922, for example, a very young Ernst Eppig, whom most of you are probably too young never to have heard of, but an amazingly intuitive and intelligent and perceptive individual who was an Estonian, eventually worked in Ireland. But in 1922, when he was very young, he published a prescient paper in the Astrophysical journal using the Vril theorem to determine the distance of Andromeda Nebula on the assumption that the nebula's mass-luminosity ratio and mass density should be similar to that of our own galaxy. And his estimate was very close to the right one for the distance. Had Eppig and Georges Lemaitre been panelists around a table that I showed just before, they might have cautioned by 1931 that Hubble's original constant seemed incompatibly high with general relativity if that theory were trusted. By 1948, Fred Hoyle would also have noted that the Hubble constant computed using Cepheid variable distances was also in conflict with the ages of stars. A century ago, the institution of Solvay conferences, relatively small, regularly held gatherings attended by widely knowledgeable experts like Planck, shown in the background here, Rutherford, Einstein, Marie Curie sitting in front here, Sir James Jeans, respectively, serving as panelists respectively in the era the witnessing the discovery of quantized radiation, radioactivity, special relativity, the structure of nuclei, or developments in astrophysics. Today we hold relatively few such meetings, like the Solvay conference, devoted to single topics of importance to our science or the implications of astonishing new finds for our field as a whole. But meetings designed to assemble experts selected for their ability to exchange ideas meaningfully in several fields beside their own could be a great help in preventing, or at least reducing, the number of harmful instabilities to which astrophysics and cosmology, as we can see, are so prone. Thank you.
That certainly was something different. Are there questions? Too overwhelmed?
Just a moment. In the stylized diagram you showed of the panel of experts, I think A through G, you said that you have to have 2 arrows connecting each person to the group to avoid sort of unstable failure to transmit messages accurately. But doesn't that somewhat depend on the size of the panel? I mean, if you changed it to a panel of 4 people, would the number of arrows go down? If you changed it to 20, would it go up?
No, I didn't say how many hours. I just said that they needed to have 2 languages that they could communicate with. I haven't looked into what the optimum number is. It really depends on the type of problem that you're talking about. And so the kind of complexity that you have on a spacecraft usually would require something of the order of 12 people. Cryogenics, optics, the experts on computer languages, things like that. So 12 would not be unusual for a panel that deals with spacecraft problems.
I didn't quite catch, I didn't catch at all, the general principles beyond or behind the work on networks by the Northeastern people. In other words, how that scales with various things.
Well, the paper that they produced is really very nice reading. It was a Nature paper, and so it was readable by a very large audience. They tried to show what you could not do as sort of very general principles. When you get down to the details of how you would control a particular network, then it depends very much on the structure of the network. Do you have to add additional switches? So for example, when I did this talk some time ago in the Netherlands, somebody said, you're violating the principle that no node should have two superiors or two inferiors. But the way that it works in the panel that I was talking about, the two superior panelists that send you messages that you compare act as a coincidence counter, more or less. So that's a switch in itself. If they give you conflicting information, then you stop and you say again, or could you explain the difference? So you can have this kind of a structure. So that's not the kind of thing that that particular article went into detail on, but you kind of figure it out on your own on the basis of some of these more general principles. But you know, they're very complicated theories that people work out. That's why not everybody does network theory. It's fairly complicated mathematics. And Cambridge is lucky in having some of the leading lights in the universe, actually, as we know it today. Right here.
Martin, let me just ask, you showed this true but nevertheless daunting diagram of all of the advisory committees.
Yeah.
I mean, if we could eliminate that and start afresh, how would the approach you're suggesting would be more sensible look? I mean, how would we go from the ideas in this room to actually funded projects?
Did you ever live in the Soviet Union?
Not that I recall.
Well, you know, you can always do things by fiat, but I mean, I think one of the advantages of a democratic system is that you listen to a number of different points of view. A disadvantage is that people often can't agree with each other for various personal problems and innate differences. Did I ever tell you about the Air and Space Museum exhibition of the moon?
I hadn't heard of that before. Do tell.
So,
You ought to write a book.
you know, I mean, each of these systems, some autocratic systems are very efficient. And sometimes they work well for a limited amount of time, but after a while, it becomes too monotonic. And so you need fresh ideas, you need to bring those in. I don't know the better system, but one ought to be aware of its various advantages and disadvantages. There is one aspect of this that Harvey will remember. When we were working on the great observatories, the associate administrator for space science and applications, Bert Edelson, kept pounding at us that we had to go to every center that NASA had, every panel that the National Academy had, and we should get them all to agree. Okay. And it seemed like an impossible task. And so we all used to sort of snicker a bit and say, well, he's he just can't make up his mind. Bert doesn't want to make a decision. No. But 30 years later, when I started seeing what Lewis Lotin and Barabashi had written, I realized you do have to get all of the arrows pointing in the same direction. And so Bert Edelson was probably right, maybe not for the right reasons, but he had it in his bones that this thing wasn't going to go forward unless everybody agreed. And so we had to get all the different levels. For example, Charlie Pellerin, who was in charge of astrophysics, had to eventually give in to his counterpart on the planetary side and said, okay, we'll make a deal. You guys can use CERTEP, as it was called at the time, Spitzer now. And let's also make a deal on Sophia, which the planetary community also were interested in. Before that, the planetary community had its own planetary exploration priorities and wasn't interested in the astrophysical one. So intelligent things do come out sometimes by trying to strive for something that will work.
Well, the Decadal Committee is our obvious forum for this kind of discussion, and some of us think it didn't work that well last time. Is there a different way we should structure it? How do you get rid of people? People, when you're working on a spacecraft and getting to work again, everybody has the same goal. When we're working on, when you're on one of those committees for making the decision of the top priorities, you all have different goals, right? You want your mission to get in there.
Yeah.
Or too much about my is there some way we can structure to avoid that? I don't see it.
You mean everybody going to the Decadal Review
and they've taken their toy that they want to get built.
Area.
Yeah.
You just have to be able to make a good case, and of course that doesn't always go, and there's a lot of politicking going along with that. You do have a central committee working on these decadal reviews. I was thinking at one time that those are not structured the way that the ones that you have for repairing spacecraft. The committees you have for repairing spacecraft consist of specialists who are able to at least communicate, okay? My feeling is that the people who are at the center of the decadal review tend to be generalists rather than specialists. Almost every review, every decadal review we've had has been led by theorists, and almost every decadal review we've had has proposed expensive engineering projects. I rest my case.
Usually at that point in the movie, it's over. Are there any other
I'll get
questions?
clobbered by theorists now. Can you protect me? You're my host.
Not in this group. Sorry.
There's a lot to think about. Going back to the panels where they have to solve a technical problem on a spacecraft, I think that I really have to think about it a lot to try to fold in our own experience from Chandra. But I think that things can be, in some ways, less complicated if you have a very stable and long-lived team that works together and actually learn to speak each other's language. Then when one person speaks, essentially the group as a whole understands. And if you have a facilitating group, which to some extent SAO provided through that program, even if everybody doesn't understand at first, that facilitating group or who's ever representing, if it's a flight director at a particular time or whatever, is able to translate what a technical expert brings in and put it back out to the group as a whole, which again cuts down the number of communications.
But language, as you point out, is really the criterion in all of these things. And language is something that is hardly ever mentioned by astrophysicists, but ultimately, you know, as our discipline becomes ever more enriched and new subdisciplines migrate further and further apart. Language changes. Words that used to have one and the same meaning, as these groups separate, change. Now then you start getting confusion when one group thinks it still understands the word, but it now has different meanings. Language is just an integral part of everything that we do. And you only have to open physical review letters to know how far physics has drifted away from what you might have known, say, 10 years ago. I mean, I get continually angry at authors because, and editors who allow the authors to do this, that they come up with a certain phenomenon which they name after a colleague who had invented it, or discovered it. But there's no description of what that phenomenon is. So now you have phenomenon named after Mr. or Miss X. And the whole paper is written by that way, and you can't understand it. Okay, and physical review letters used to be something that I subscribed to and really enjoyed. I mean, I really waited each week to get it. And there'd be maybe 20 articles at most initially, or 15, 12, I don't know. It was fun to read. And you could do that, and now you can't do that anymore. So what the physics community has done has been to try to invent other journals that do facilitate communications, and they bring important problems that have been published in physical review letters and gotten the symbols which show that they're particularly interesting topics. Bring those out, bring them all together, and have those then in a separate journal online where you can find them. And that's very helpful. But you have to keep on doing this, bringing groups together, otherwise you won't have a world view. I mean, that's what we really all are here for. We have our own problems we're working on. But we do want to understand the universe as a whole, including planets and asteroids and everything, and dark matter and dark energy, see what those interactions are.
One last question.
Well, sort of a remark about language. One thing I think we're seeing now is the encroachment of what you might call computer intelligence into our, I mean, particularly in cosmology, right? The current cosmology model is essentially an MC-MC optimization. And if you have such an optimization, you can't necessarily put into words an explanation of why, why it works. Even optical design is done this way, right? When you design an optical instrument now that has a number of lenses and has, say, 30 parameters, and you optimize it in a computer, you can't necessarily explain in words why it works. It just does.
Yeah.
Right? And the computer found it, in a way that is totally without language. And maybe you can make up explanations for parts of it, but the whole may not necessarily be comprehensible as language.
True. But the persons who build that device usually have also, for now at least, some intuition about what is likely to improve the design or not, and how it works. Without the intuition, you could have a machine that you had optimized, but it would be kind of baffling, right? So one would probably try to see whether there was some inherent principle that, if not explained, but at least put into a formula, a recipe, something that might be useful to do next time around if you wanted to have a shortcut. So,
in chess, this has already happened, right? The world's chess champion is a computer, and if you say, well, why did the computer do this? There's really no explanation. It's just a really good move, and the way people think about how you play chess were not the way that computer was thinking about.
Well, that's correct, and that's mainly because we don't think fast enough. So there are other techniques that take advantage of very fast searches that the brain is unable to accomplish during that time. And so you can find an optimum solution just by trial and error if you work very fast. Yeah, I'm not saying that language is everything, but it certainly so far has been the cement that has held astronomy, astrophysics, cosmology together. And we should respect it. And we should, I think, in our journals try to insist that authors make it easier for people to read by giving reasonable introductions. And if you look at Nature, the first paragraph is usually, I understand it at least, very heavily edited by the people at Nature to try to put things in terms that at least fellow professionals within the discipline that in which that paper is written will understand. And sometimes even so, let's say a biologist can understand an astrophysical paper. So it happens. It's good when it happens, right? I mean, you get pleasure out of it.
Great, Mark. Well, after we thank Martin in a moment, I would just ask that the inflation theorists leave first, and then we can safely escort him. Let's say.